All right, so what we really want to do from this Hooke's Law lab is we want to derive an equation for elastic energy, okay? And if you notice, what we've done is we've graphed force and some kind of distance, right? Which in this case was the displacement of the spring, okay? So in this picture here, you can see that the further I stretch this spring, right, we know that that's going to store more energy, right? Because like we talked about last class, right? Like if you overstretch the rubber band into my face, that's scarier, meaning that stores more energy. There's more potential for change to happen, okay? So the other part of the graph that changes, besides when I go from here to here to here, right? Obviously, the displacement is increasing and the force is increasing, but also the area under this curve is also increasing, okay? All right, so if I look at this area here, right, it's a triangle. Okay, so this area is going to be basically a triangle, so 1/2 base times height, okay? And so that's 1/2, the base is the spring stretch, okay, and the height is the spring force, all right? And most commonly, then we would replace this with Hooke's Law, okay? We wouldn't worry about the negative, right, because it's just energy. All right, and so then what I end up with is 1/2 k delta x squared, okay? And then since that is what is increasing here, right, that area is increasing, we're going to infer, and from the units, that this is the spring or elastic energy, okay? All right, so this elastic energy equation, 1/2 k delta x squared, okay, so that's a new equation that you'll need to know. It's on the equation sheet. All right, and looking at units, okay, 1/2 doesn't have a unit. The spring constant, remember, is newtons per meter, and that's a meter squared, okay, the displacement. So that's going to cancel, so we get these units of Newton meters, similar to torque, right? But remember, torque had a direction associated, so it's not quite the same thing, okay? This we call a joule. Okay, you might remember that from freshman year. Or capital J named after James Joule. Oops. All right, so a Newton meter is a joule. So anytime you see a Newton meter, the equivalent unit is a joule, unless it's torque, right? Torque is not a joule because torque is a cross product. It's a directional thing. Okay, all right, so the units of energy is going to be joule. All right, but the main thing to understand is the area under F versus X is energy, because that's going to come up again and again.